Asteroid impacts have always been a fascinating concept. Although uncommon, even today we see news articles of asteroids reaching the surface of Earth. And they make for interesting subjects of disaster movies. Why? Well, they are likely to have caused the mass extinction which wiped out 76% of all species on the planet 66 million years ago. Was this a one-off? Or could such an event happen again? And if a large asteroid was on course to strike Earth, could we prevent it and survive using current technology? I'm Alex McColgan and you're watching Astrum. Join me today as we learn about the DART mission, humanity's first attempt to change the course of an asteroid to protect our world from future planet-ending threats. Major impact events have significantly shaped Earth's history. Going back to the very early solar system, one of the biggest impacts in our history may have formed the Moon, where a planet-sized object named Theia collided with the young Earth. As time progressed, we may now have oceans full of water thanks to collisions with asteroids. And since then, asteroids have also potentially caused several mass extinctions. One of the most well-known impact events left the Chicxulub crater, which is believed to have caused the extinction of dinosaurs 66 million years ago. There is an inverse relationship between the size of an object and the frequency of such events. Small objects frequently collide with Earth, while large object collision events are very rare. And as the solar system ages, large asteroid impacts become less common. You see, when asteroids collide with something, they either fragment into smaller chunks, or they get integrated into the larger bodies, like the planets. It is estimated that Earth gains 15,000 tons per year this way from meteors entering its atmosphere. Impacts actually happen all the time on Earth, a lot more than you may think, but most are barely noticeable. Meteors, or shooting stars, are tiny objects with sizes ranging from sand grains to stones only a few centimeters across. These burn up as they enter Earth's atmosphere. So, how many do you think hit Earth's atmosphere on a daily basis? The figure may surprise you. 25 million. And guess what the biggest meteor is likely to be on any given day? 40 centimeters across. The biggest one on a yearly basis is around 4 meters, and every century we get one that is at least 20 meters across. The objects that manage to survive the Earth's atmosphere and land on the surface are called meteorites. These have to be somewhat larger than normal shooting stars to survive, and most of the time what's left of the object upon reaching Earth's surface is about the size of a brick. These objects cause large trails in the sky with spectacular colors, known as fireballs. Every 2,000 years or so, a meteor about 100 meters across hits Earth, blasting through the atmosphere, causing significant damage to the area from the impact itself, but also from the airburst associated with it. And then you have objects large enough to threaten civilizations on Earth, objects over 10 kilometers, that only come around once every several million years or so. The chances of anyone alive today encountering such an event are very close to zero. One of the good things about larger objects is that they are also easier to spot, and scientists think they know of all nearby asteroids above the size of 10 kilometers with a very high degree of certainty. But smaller, less easy to spot meteors are still a big threat on a more local scale. About 1,500 people were injured in 2013 when the Chelyabinsk meteor exploded over Chelyabinsk in Russia. Around 7,200 buildings across 6 cities were damaged by the explosion's shockwave. Luckily, no one was fatally injured during this incident, but imagine if such a disaster were to happen in a highly populated region. Needless to say, the results would be catastrophic. This is why it is very important for us to be able to detect and prevent this before it has a chance of happening. One of the ways to do that is for us to find and track objects in space that might be a threat. And we are doing this faster and more efficiently than ever before. We've discovered over 20,000 new potentially dangerous asteroids in just the past 2 decades, with about 30 new discoveries added each week. Most of them have harmless orbits, but what would we do if we ever found an asteroid that was on a collision course with Earth? This was what NASA was trying to find a solution for with its DART mission, or the Double Asteroid Redirection Test. DART was a joint project between NASA and Johns Hopkins Applied Physics Laboratory, with international partners in Italy, Japan, and the European Space Agency. Its goal? To try to redirect an asteroid's path by colliding a spacecraft with it. Before DART came along, many different ideas were floated about the best way to prevent an asteroid collision. If we had enough warning, and if the asteroid was small enough, we could send a spacecraft to ride along with an asteroid to act as a gravity tractor. Over time, the presence of the spacecraft could gravitationally influence the asteroid just enough to redirect its orbit slightly out of the path of Earth. It sounds a little far-fetched, but in 2015, NASA published an article on their webpage stating that this was a workable solution. Perhaps a more well-known idea is that of just sending in a nuke. Asteroids aren't very densely packed, so exploding them into tiny pieces ought to be easy enough to do. But although this idea was popularized by films like Armageddon, it might not actually work as well in practice, as the momentum of the asteroid would be largely maintained even as its form shattered into pieces. If the resultant pieces were big enough, this would have the unfortunate effect of turning a metaphorical bullet heading towards Earth into an equally deadly shotgun spray. A third idea was about sending reflective mirrors to an asteroid. It's a well-documented fact that as comets pass by the sun and heat up, they frequently start outgassing, giving them added propulsion away from the sun. Spacecrafts with mirrors that travel to an asteroid and reflect its sunlight onto its surface at the right location could attempt to cause similar outgassing, letting the asteroid itself propel itself out of the path of Earth with its own released gases. But the creators of DART settled on perhaps the simplest solution, and one that we had successfully pulled off before with a comet: to directly impact the asteroid. Not to blow it up, but to hit it just hard enough to knock it off course. The kinetic plan was settled on, but mission planners needed to greenlight a suitable test asteroid to hit, and so scientists settled on Dimorphos. This asteroid was first discovered fairly recently in 2003. It is the small moon in a binary system, orbiting around the larger Didymos, which was spotted in 1996 by the Space Watch project in Arizona. Dimorphos is only 160 meters across, which is much smaller than the 780-meter Didymos, and has an orbital period of 11.9 hours and maintains a distance of around 1 kilometer from its larger neighbor. The system orbits the Sun every 2.1 Earth years and made its approach to Earth in October 2022, coming within 10.6 million kilometers, the closest it's been since 2003, meaning this was the perfect time to visit it. It was this closeness that caused NASA to choose Dimorphos as their target. It was relatively easy to get to, but crucially, it was not so close as to be on a collision course with Earth. Scientists were confident that even once knocked off course, the Earth itself would not be in any danger. With their target set, NASA needed to build the perfect spacecraft to perform the deflection. Compared to other spacecraft, DART doesn't have a lot of frills. It's about the size of a refrigerator and weighs just 610 kilograms, which is minuscule compared to Dimorphos' estimated weight of 5 billion kilograms. DART has one payload, an aperture camera called Draco, short for Didymos Reconnaissance and Asteroid Camera for optical navigation, as well as sensors and an autonomous navigation system. It also comes paired with a small secondary spacecraft called LiCiaCube, making it a binary spacecraft visiting a binary system. Built by the Italian space agency ASI, LiCiaCube is a small CubeSat with its own autonomous navigation system designed to separate from DART 15 days before impact. LiCiaCube is tasked with recording the impact and its aftermath with 2 optical cameras named Luke and Leia. Yes, you heard that correctly, Star Wars fans. The LiCiaCube weighs just 14 kilograms and is only about 30 centimeters long. It would fly by the asteroid system using its own autonomous navigation system. The DART spacecraft was also designed to be running autonomously. Due to the latency between sending and receiving instructions caused by the distances between Earth and the spacecraft, DART needed to locate the moonlet, detect a perfect spot for the impact to happen, and then aim itself appropriately. This is where DART's smart nav came in handy. This autonomous optical navigation system could identify and distinguish between the two bodies and detect the target, and then direct the spacecraft towards it. And surprisingly, all this would happen within only an hour before the impact. After blasting off on the 23rd of November 2021 on a SpaceX Falcon 9 rocket, DART spent the next 10 months in transit. In the 4 hours leading up to the impact, at a distance of 90,000 kilometers, DART's internal navigation system took over, and 90 minutes before impact, its smart nav system put the spacecraft on its final trajectory. When DART was 24,000 kilometers away, Dimorphos became visible on camera, taking up 1.4 pixels. This is one of Draco's last images, where you can see both Dimorphos and its parent asteroid in the same frame. As DART hurtled closer to its target at a speed of 22,000 kilometers per hour, Dimorphos and its potential impact site came into spectacular view. In this image, taken just 3 seconds before impact, you can really see how Dimorphos is a loose pile of rubble, essentially left over from the solar system's birth. This remarkable photograph is DART's final fully transmitted image. It was taken at a distance of 12 kilometers, a mere 2 seconds before impact. For reference, the scale is roughly 3 centimeters per pixel. And here, finally, is DART's last, partially transmitted image. The downlink was interrupted by DART's previously scheduled, shall we say, disassembly. As strange as it sounds, this is my favorite of these images. Its incompleteness seems to capture the drama and intensity of the moment, as though freezing for all time the breathtaking instant when DART completed its 17.5 million kilometer journey in the blink of an eye. To the very end, DART did what it was designed to do with incredible precision, and it's a testament to the ingenuity of those at NASA. Here is the entire sequence sped up and played as a time-lapse. The video you see corresponds to the final 5.5 minutes of DART's final trajectory. As you'll notice, some of the images look a bit blurred. That's because DART's ion thrusters came into play, causing vibrations to the spacecraft and its camera. This sequence is incredible to me due to the speed involved. It hits such a tiny object, and I'm astonished some of these images are in focus at all. Imagine how quickly the camera had to adjust to the rapidly approaching object. Now, I'm sure you're itching to know whether the impact was successful. To relieve you of the suspense, the answer is yes. In fact, the early results have surpassed expectations. Before DART's kinetic impact, NASA defined success as a change in Dimorphos' orbital period of at least 73 seconds. Yet, based on what we know so far, the data shows that DART shortened Dimorphos' orbit by a full 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes. Even with a margin of error of plus or minus 2 minutes, that is 25 times NASA's benchmark, a truly remarkable outcome. The impact released 19 gigajoules of energy, the equivalent of 5 tons of TNT, and blasted a crater up to 150 meters wide in the asteroid's surface. Pretty big considering the moon was only 160 meters to begin with. It was also enough to change the shape of Dimorphos' orbit and the asteroid itself. Dimorphos' orbit was originally very circular around Didymos, but after DART hit, this path became more elongated. The orbital time also continued to drift over the next few weeks, before settling on 11 hours, 22 minutes and 3 seconds. As for the shape, before the impact, Dimorphos had what is known as an oblate spheroid shape, a bit like a slightly squashed ball. Afterwards, it had become a triaxial ellipsoid, similar to an oblong watermelon. It's fascinating to consider the forces that must have been at play for this change of shape to occur. It also highlights the fluffy nature of asteroids like Dimorphos, being so loosely tied together by gravity. It increases the capacity for shape changes like these to happen if hit with the right impact. Not to worry though, even with large margins of variability, scientists know that even with this collision, the orbit of Didymos won't change enough to ever cross paths with Earth. But if there was an Earth-bound asteroid, this little nudge early enough in advance can impact its orbit enough to take it off a collision course. But why did the impact shorten Dimorphos' orbit? Well, due to orbital mechanics, the crash pushed Dimorphos closer to Didymos, which in turn sped up its orbit. Scientists confirm this finding through observations from optical telescopes here on Earth, including the Southern Astrophysical Research Telescope in Chile. SOAR also happened to capture some of the very best images of the encounter, including this breathtaking photograph of a 10,000 kilometer trail of debris 2 days after the impact, making it look like a comet. Because Didymos is a 2-asteroid system, its brightness fluctuates as Dimorphos passes through the shadow of its parent asteroid and out again in front. By tracking the light curve, scientists can calculate the speed of Dimorphos' orbit. These results were further supported by radar data collected by observatories in California and West Virginia. DART and Earthbound telescopes weren't the only cameras watching the event though. The closest images of the crash scene were captured by Lichia Cube, and they are phenomenal. As I previously mentioned, Lichia Cube separated from DART 2 weeks before impact to conduct its own flyby using autonomous navigation systems. 2 minutes and 45 seconds after DART's impact, Lichia Cube flew past Dimorphos to photograph the impact site with its evolving plumes and ejector. Here is an action-packed image of Dimorphos after the event, with Didymos overexposed in the foreground. Notice the huge plumes of material emanating from Dimorphos. Some of them seem to be spiraling, almost like tendrils of a vine. This indicates that the material changed directions as the plume grew. We think this phenomenon may be caused by the composition of the asteroid, as impact tests on finer sediment mixed with coarser debris sometimes yield similar ejection patterns. This is a more distant image, also captured by Lichia Cube, with Dimorphos on the rightmost side. Notice how the asteroid itself is barely visible due to the huge clouds of material splashed up by the impact. Hubble and the Webb telescope also got in on the action of imaging the aftermath of DART's impact. Here you can see a spectacular series of images from Hubble showing the progression of the plumes in size and number. Notice how some of the plumes look like rays emanating from the asteroid. Strangely, some of these rays appear curved. Why? As of now, NASA isn't sure. While Hubble has observed the impact from the visible spectrum of light, the Webb telescope captured its own images from the infrared spectrum. This is pretty impressive, since Dimorphos was traveling 3 times faster than Webb was meant to be able to track. The time-lapse you are looking at starts right before impact and continues until 5 hours afterwards. Notice the sudden flare of light, coinciding with the material released from impact. I also love how the Webb images give you a great sense of the spiraling plumes emanating from the asteroid. Over the coming weeks and months, scientists will continue to study the data from DART's impact. But the real investigative work will be carried out in the future by Hera. Hera is a follow-up mission currently being carried out by the European Space Agency that launched on the 7th of October 2024 and will reach the Didymos system by 2026. Carrying a sophisticated payload of instruments including cameras, a spectrometer, and altimeter, once it arrives, Hera will intricately document the size, shape, and composition of the crater left behind by DART's impact. Most exciting of all, Hera will conduct observations of Dimorphos' internal and subsurface structures. This model will not only advance our understanding of the binary Didymos system itself, but provide a more nuanced understanding of how NEO's physical characteristics influence the transfer of momentum, as well as how kinetic energy transfers to an NEO and ejected materials. All of this will allow for a greater understanding of DART's kinetic impact and provide a useful guideline for improving deflection technologies in the future. So combine that with NASA's missions like NEO-Surveyor, which aims to discover at least 90% of asteroids 140 meters in size or larger, and it feels like humanity for the first time has actively reduced its chances of being hit by the kind of world-ending impact that likely wiped out the dinosaurs. NASA already keeps track of most near-Earth objects, but some asteroids like dark comets are harder to see if they don't reflect much visible light. NEO-Surveyor is proposed to launch in 2028 and will scan the solar system for such objects by taking infrared readings, detecting hard to spot asteroids by seeing the heat they radiate when they are warmed by the sun. It will also be able to spot asteroids that approach Earth from our blind spots, such as ones coming directly from the direction of the sun, which ground-based telescopes might miss due to the glare. With even the hardest to see NEOs being detected, the technology proven by DART will be a shield that can keep our world safe. So there we have it. Everything you could want to know about the DART mission. Right now we've barely scratched the surface of deflection technologies, but if you look at what this mission has accomplished, it appears the future of planetary defense has taken a bold and promising first step. So, do you think this mission was worthwhile? Do you think we'll have to use this technology within our lifetimes? Let me know in the comments. If you've ever looked up at the night sky and watched a comet streak by, you will know of the wonder of watching one of these celestial visitors. Often seen with awe or fear throughout humanity's history, these bright-tailed objects in our skies were known as harbingers of change. And yet, in the last 50 years, the tables turned on these icy wanderers, and it went from them coming to visit us to us being able to visit them. Scientists had long wondered about the nature and origin of comets. Where had they come from? How were they formed? In 1986, the first probe was launched to image Halley's Comet, and scientists began to find answers. But to truly understand comets, it would take more than photographs. A more physical approach would be needed. Between 1999 and 2005, 2 probes were launched. Their mission was to interact with comets in ways that had never been attempted before. One would bring collection equipment that would allow it to scoop stardust right from the comet's icy tail to help scientists analyze the chemical makeup of these frosty harbingers. The second would take a more forceful approach. Rather than quietly collecting a smattering of space dust, the second probe would crash headfirst into the surface of the comet itself, exploding with the force of 5 tons of TNT, to see what could be learned from the resulting crater and debris. And yet, although these 2 missions were 2 different comets, through chance there was one comet that unexpectedly brought them both together, Tempel 1. I'm Alex McColgan and you're watching Astrum. Join with me today in today's Supercut as we explore the explosive story of Tempel 1 and how the Stardust and Deep Impact probes both were needed to help discover what lay at the heart of this space-borne nomad. In the early 90s, comets were still a bit of an enigma. By 1999, 8 different spacecraft had been launched to investigate comets in our solar system, with 5 of them having flown by Halley's Comet in 1986. But beyond that, only 2 other comets had been visited, Comet Giacobini-Sinner in 1985 and Comet Grigg-Skellerup in 1992. And while some fascinating photos and dust samples had been taken as close as 200 kilometers from some of these incredible celestial bodies' comas and tails, comets still had many mysteries. What was their internal structure like? What were they made from? And how had they formed in the first place? In 1999, NASA scientists proposed the plan to hopefully answer some of these questions. It would be difficult to understand the internal structure of comets by simply looking at their surface. To know what was going on, scientists would need to dig a little deeper. Their plan was to create a crater in a comet using an impactor spacecraft, which would collide with the comet at high speeds. As they would know the mass of the impactor and the speed it was traveling at, they could calculate from the size of the impact crater valuable information about the comet, whether its surface was a loose aggregate of dust and ice, or whether it had a hard, frozen shell, for instance. The comet they wanted to target was a short-period comet called Tempel 1, which had a nucleus of 8 kilometers long and 5 kilometers wide. Scientists weren't exactly certain what would happen when the impactor hit. Perhaps the impactor would punch straight through, like hitting a snowdrift, and not really create a crater at all. There were many theories, but scientists were eager to find out which was correct. NASA approved the project, giving it a budget of $330 million, and named it Deep Impact. You might have thought that this was a reference to the 1998 Hollywood film of the same name, but apparently the names for both the project and the film had been come up with independently around the same time. Quite the remarkable coincidence if so, as Deep Impact, the film, was about scientists trying to blow up a meteor that was on a collision course with the Earth by flying a spacecraft to it carrying nuclear warheads. There certainly seemed to be some similarities to the NASA mission, especially as NASA scientists worked on the film. I don't entirely buy NASA's claim of a coincidence. Although, fortunately for the Earth, there were some differences between the film and the mission too. Tempel 1's orbit was nowhere near the Earth's, and given the size of the impactor compared to the comet, there was no chance of knocking it off its current trajectory by more than a centimeter or so. It would be more like a fly hitting the front windscreen of a large vehicle. Additionally, nukes would not be necessary to create a crater on Tempel 1, or any kind of explosives for that matter. The sheer speed and kinetic force the impactor would have when it collided with the comet's surface would be enough to create the crater, which some predicted would be roughly 100 meters across and 30 meters deep. With the mission going ahead, scientists began work on the Deep Impact spacecraft. The spacecraft was actually made with two parts: the payload and another larger mothership to carry it and record the result of the impact. The second section was called the flyby. It weighed 601 kilograms, was 3 meters long, and housed scientific devices, solar panels, a debris shield, and two powerful cameras, the high-resolution imager and the medium-resolution imager. These would take photos of the comet after the impact, as well as help with navigation. The impactor itself was smaller, only 372 kilograms, but it was still smart and housed a camera of its own. This camera, the impactor targeting sensor, would take photos of Tempel 1 right up until the moment of impact, streaming back the images it collected to its parent, Flyby, which would then relay the images to Earth. There was considerable public interest in the mission, which NASA encouraged in 2003 by getting members of the public to submit their names to be recorded on a CD, which was placed on the impactor. Roughly 625,000 names were collected in this way, to be carried directly to Tempel 1's surface. On top of that, NASA timed the impact to take place on the 4th of July, American Independence Day. While this may have been because it was one day before Tempel 1's perihelion, and its proximity to the Sun may have produced clearer images, I suspect that the more likely reason for this date was that American scientists liked the idea of a large cosmic firework. Deep Impact launched on the 12th of January 2005 on a Delta II rocket. But then a problem hit. Within a day of leaving the Earth's orbit, Deep Impact's onboard computers switched itself to safe mode, which it would only do if there was a fault. Something on board was apparently overheating. This gave scientists a bit of a scare, but fortunately the cause of the problem was quickly found to be a minor programming issue. Acceptable heat tolerances had been set too low, so Deep Impact thought its thrusters were overheating, when in reality they were just fine. Engineers corrected the issue, and Deep Impact was able to properly begin its mission. The spacecraft spent the next 6 months traveling to its rendezvous point with Tempel 1. In that time, it traveled 429 million kilometers. It had to course correct twice on the journey, but this was actually impressive, as it had originally been planned for there to be 3 course corrections. One was just so precise that the other was deemed unnecessary. On the 25th of April 2005, Deep Impact caught its first glimpse of Comet Tempel 1. Of course, NASA scientists couldn't manually guide Deep Impact as there was a several-minute signal lag. Deep Impact and Tempel 1 were now roughly 130 million kilometers away from Earth, more than twice the closest distance between Earth and Mars. Deep Impact's smart onboard programming would have to guide it in for the final leg of the journey. On the 29th of June, the impactor successfully released from the flyby and positioned itself into the comet's flight path to crash into it head-on. This was done for a few reasons. First, the front of the comet was in sunlight, which would allow for better pictures to be taken. Second, it would allow a greater accumulated speed to be reached, resulting in greater kinetic force. And on the 4th of July 2005, just 1 second out from the anticipated arrival time, the impactor hit. And what a magnificent spectacle it produced. Scientists were thrilled that they had struck so accurately. Deep Impact's payload had been traveling at 37,000 kilometers per hour and had struck with a force of 19 billion joules of kinetic energy. This produced the bright flash you see here, the energy of which is roughly equivalent to 5 tons of TNT. This flash was much brighter than scientists expected. It lit up the surface of Tempel 1. However, ironically, the success of the first part of the mission caused an unexpected negative side effect. A large dust cloud was kicked up by the impact, which obscured the flyby's view of the impact crater. Dust outgassed from the comet for the next 13 days, peaking 5 days in, which made it hard to see the results of this interstellar bullseye. Although it did offer some interesting insights into the internal pressures going on inside the comet. Around 5 million kilograms of water and between 10 and 25 million kilograms of dust were ejected from Tempel 1 in that time. Fortunately, scientists were able to rely on other eyes, at least to capture images of the explosion. The collision had been observed through numerous other telescopes on or around Earth, including Hubble, Swift, and even many amateur astronomer telescopes. Still, this was a serious problem. Although this outgassing was fascinating to record, the primary purpose of the Deep Impact mission was to take photographs of the crater caused by Deep Impact. Without images of the result, many of the questions about Tempel 1 would remain unanswered, like about its structure and composition. Like a partially unwrapped gift, Tempel 1 had been opened, but it had not yet been seen what lay inside. Some other craft would be needed to complete Deep Impact's unfinished mission. Fortunately, another craft capable of doing so had already been launched, and, having completed its own previous mission, was now drifting serenely through space. It was about to receive another task. It's time to talk about Stardust. Let's go back to the late 1990s, when cometary science was even more patchy. Although by this point we had sent 6 probes up to visit these enigmatic celestial bodies, not very much was known about their origins. It was believed at the time that comets were foreign visitors to our solar system, older than the Sun, having been formed from the loose pre-solar grains of dust that orbit other stars, before drifting through space towards us, only to be caught up in the Sun's gravitational pull. It was believed that this theory could be confirmed by traveling to one of these comets and picking up some of this loose dust, or stardust, that surrounds them in space. By examining the isotopic composition, scientists would be able to tell if it was unusual when compared to the dust given off by our own star. However, this was a challenging mission. As is often the case, it came down to a question of speed and energy. Comets travel through the inner solar system at speeds reaching 160,000 kilometers per hour. While it was possible for a probe to try and match that speed and come up alongside it, this had to be done without needing too much fuel, or the weight of the craft would be too heavy and thus too expensive to get into space in the first place. Initially, Stardust had nothing to do with Tempel 1. For this mission, scientists selected a comet known as Wild 2. They believed that they would be able to get Stardust alongside Wild 2 at a relatively low velocity. However, this velocity would still be around 6.5 kilometers per second, or 23,400 kilometers per hour. As you can imagine, catching even particles at that speed would be extremely challenging. Although particles would likely not do too much damage to Stardust, being too small to really impact it, it would do irreparable damage to the particles themselves. When an object crashes at 23,400 km per hour into a surface, the odds of it keeping its original shape and structure are incredibly small. Scientists would not learn much about the structure of these particles if they smashed those particles into pieces, not to mention the warping effect all that kinetic energy being suddenly converted into thermal would have on the molecular bonds involved. So, what was their solution? What was their mechanism for catching objects traveling at those speeds? Well, much like how an airbag softens the blow for you if you are involved in a car crash, scientists realized that they would need an airbag of their own. Something that would not halt the particle all at once, but would reduce its speed over a longer distance, thus reducing the amount of crushing deceleration involved. For this, they found an incredible material that was basically air, solid air. They decided to use aerogel. Aerogel is a fascinating substance that was discovered in 1931 by Samuel Kistler when he made a bet with fellow scientist Charles Learned about jelly. As you've probably seen if you've ever made it yourself, jelly is formed of two parts. Firstly, a relatively solid structure that acts like a kind of sponge, and secondly, water. When you add water to solid cubes of dense jelly, it absorbs the water and expands into the wobbly substance we are familiar with. If you were to extract the water, the solid part of the jelly would normally contract again. Kistler's bet with Learned was to be the first one to remove all of the liquid from the jelly without making it shrink. In short, to make a jelly that was entirely filled with air, an air jelly. Without going into all the details, Kistler won his bet and at the same time invented the first aerogel. Aerogel is a fascinating substance as it is usually over 99% air and yet has the structural strength to support bricks. Nowadays it tends to be made from silica composites rather than jelly, but can be made from a wide range of materials. It is incredibly light and is, strangely enough, an even better insulator than regular air. And most importantly for stardust, when particles hit it, it would offer just the right amount of resistance to slow down the particle without denaturing or destroying it. The trails left behind in the aerogel would also be useful for scientists to spot where a particle had been captured. Stardust was fitted with a tennis racket-sized aerogel collector tray made up of 90 blocks of aerogel 3 cm thick, with over 1,000 square centimeters of surface area, which would be deployed from inside the main body whenever sampling was to take place. Stardust would also capture from the interstellar medium to allow comparisons and to learn more about the dust in our own solar system. Once it had collected these samples, it would store them on a sample return capsule, which would be fired back towards the Earth for re-entry and collection. This SRC was 80 centimeters by 50 centimeters, weighed 45 kilograms, and came fitted with an aero shield, navigation recovery aids, and a parachute. Also on board Stardust was a navigation camera, a cometry and interstellar dust analyzer, and a dust flux monitoring system, among other scientific devices. The probe launched on the 7th of February 1999 and spent the next 5 years traveling through space, passing the asteroid 5535 Anne Frank along the way, which it took some photos of. But on the 2nd of January 2004, it finally arrived at its target, Comet Wild 2. And what it found was immediately extraordinary. Scientists had not expected much from Wild 2. Some NASA scientists described their expectation of it to be a rather bland object looking somewhat like a black potato. However, this is not what they found. Instead, the surface of Wild 2 was covered with spiky pinnacles hundreds of meters tall, cliffs, massive holes jetting dust and gas out into space, even on parts of the comet that were pointed away from the sun, and thus were expected to be less reactive. In short, the surface of the comet was unexpectedly alive and self-renewing. Something else was just as notable for its absence: craters. Unlike almost every other body in our solar system with surfaces exposed to space, there were no craters on the surface of Wild 2. This puts it in stark contrast to places like Mars or our own moon. Given the period of time Wild 2 is thought to have existed, it surely must have encountered other objects which impacted with it. So where had these craters gone? It shows that a comet's surface can either be self-renewing or active. reducing signs of visible craters over short time frames, astronomically speaking. And of course, during this flyby, Stardust had its aerogel collector exposed, and it was rapidly collecting dust samples. Just listen to the frequency in which dust struck the spacecraft. The samples were carefully stowed away, and upon reaching the vicinity of Earth, Stardust ejected the SRC. The angle of approach had to be just right as it was traveling at tremendous speed. If the approach angle was too low, it would just skim off the atmosphere and fly back into space. If the angle was too high, the heat would disintegrate the capsule. So it was with great relief that the DC-8 NASA airplane monitoring the sky saw it approaching at just the right second and just the right angle. The SRC landed in the Utah desert where it was recovered, everything having worked and deployed just as it was designed to. And taking the samples back to the lab, scientists learned another completely unexpected fact about Cometville 2. It was not a visitor to our solar system at all. Unlike what had previously been believed, Cometville 2 had not originated from another star. It had been born from our own. By comparing the isotopic composition of the particles Stardust collected with the samples from our own solar system, it was proven that Cometville 2 originated from the solar system. And contrary to what all the ice on its surface might lead you to believe, the rock at its center was formed under white-hot conditions. Chondrules and calcium-aluminium inclusions were both found among the samples Stardust collected. These are structures that only form under incredibly hot conditions and can be found in other asteroids between Mars and Jupiter. So scientists had to rethink their theory that comets formed in cold conditions at the edge of solar systems, even if they do spend some time there. Both fire and ice go into making comets. And thanks to the careful, delicate way that the particles had been collected, scientists were able to find out one last surprising thing: the amino acid glycine. Amino acids are the building blocks that make up proteins that are vital for all living things. Although this does not mean that there was anything alive on Cometville 2, this does lend weight to the idea that it was from comets such as this, crashing into our Earth millions of years ago, that life's first building blocks found their way to our planet, which I'm sure you all agree offers a tantalizing glimpse into our own origins. Given all these discoveries, you might have been forgiven for thinking that Stardust's work was done. But NASA is always reluctant to waste perfectly good spacecraft if they have more to give, and Stardust still had fuel in the tank. And so, when the question arose in 2006 of how NASA could capture that close-up image of Temple 1, Stardust's name was put forward. This would prove to be an interesting opportunity. Stardust was calculated to have enough fuel to make a 6-year journey around the solar system to arrive at Temple 1. This would represent the first time a comet was visited and then revisited years later, providing an intriguing chance to see how Temple 1 had evolved over the intervening years. Deep Impact only imaged about 1/3 of Temple 1's surface as it flew past, but even that was enough to identify fascinating geological features: layered terrains, smooth flows that contrasted sharply with the rougher terrain around them, crater-like vents and cliff faces. It would be incredibly insightful to see how these had changed in the time Temple 1 had orbited around the Sun. Stardust would be able to take images of things previously unseen, giving even greater coverage of the rich geological history of the comet. There were other advantages to using Stardust. It would be significantly cheaper to use equipment that had already been launched than to develop and launch something new. Stardust shielding was even designed specifically with cometary exploration in mind, which certainly came in use for reasons I'll go into later. It had all the camera equipment it needed to take precise images. And so, Stardust was approved and was given a new name to match its new assignment: the Stardust New Exploration of Temple 1 mission, or Stardust Next. Of course, achieving this goal wouldn't be easy. Course corrections had to be made years in advance to conserve fuel and make sure Stardust arrived when it was supposed to. This made things complicated, given that Temple 1 didn't just remain static as it traveled. it spins once every 40 hours. So it wasn't just a case of figuring out how to get Stardust to meet up with Temple 1. NASA had to make sure it happened when Temple 1's impacted side was facing the Sun and facing Stardust once Stardust flew past. In effect, even though Temple 1 was not easy to see clearly, they had to calculate all the spins that Temple 1 would make a full year ahead to ensure the arrival time matched up. With Stardust's diminished fuel reserves, there would be little room for error. Incredible precision and excellent models would be required. As such, NASA enlisted the help of dozens of observatories around the globe. Temple 1 was little more than a tiny dot in the night sky, thus it was impossible to track through its surface features, which were indistinguishable at that distance. However, its asymmetric shape meant that its brightness fluctuated as it traveled, dimming as a narrower profile was pointed our way, then brightening as the wider profile rotated into view, in regular intervals that allowed a detailed model to be created with a high degree of certainty. Scientists counted the spins as Stardust traveled. 1, 2, 3, knowing that if they missed a single count, it would potentially mean the failure of the primary mission objective. Their model needed to be perfect. Stardust traveled for years through space, engaging in one Earth gravity assist and multiple laps around the Sun before timing its final maneuver a full year before it would arrive at Temple 1. The burn would alter its arrival time by a small yet significant 8 hours. Stardust was now locked in. A year later, as it closed in on the comet, Stardust shields began to detect sounds as tiny particles began clattering off it. Temple 1 was still ejecting dust and small rocks into space. Stardust was hit dozens of times. Although these rocks were tiny, only a millimeter at most, some of these hits had enough force to go through the front of Stardust, cutting through a graphite cyanide honeycomb sheet as thick as your finger. Still, Stardust survived the barrage, and on the 14th of February 2011, Stardust made its flyby. It passed at a distance of 181 kilometers and took 122 images. I find it amusing that scientists waited for another holiday for a Temple 1 visit. They'd chosen Independence Day for their initial impact. Here, on a less violent visit, they chose Valentine's Day. Scientists had to wait for hours for the images from Stardust to arrive back, but when they did, NASA saw that they'd managed another bullseye. They'd correctly predicted the rotation of Temple 1 to an accuracy of a single degree. Right on Temple 1's surface was the crater that had been left by Deep Impact's payload. The mission was a success. From the images Stardust took, scientists were able to calculate that it was approximately 150 meters across, so 50% larger than they were predicting. From this, they learned that the surface of Temple 1 was a very fluffy material, made from more dust than was expected, and finer in substance than a powdered snowbank. The surface was incredibly porous. In fact, they were able to estimate that 75% of the comet was actually empty space, the whole thing held loosely together by gravitational forces. From analysis of the plume that had been ejected from Temple 1 after the impact, scientists were able to identify several interesting material components, including clays, silicates, sodium, and even organic material. While not life itself, these heavily rich carbon materials may have been carried to Earth by comets in the past, providing the vital materials that make up life here. Not only that, but they were able to see other changes that had taken place on Temple 1's surface. 3 pits that had formerly existed had merged to become one. A cliff face had eroded back around 20 to 30 meters. This indicated that Temple 1's surface was a dynamically changing place, leading to interesting questions about how these formations had formed in the first place that scientists could now puzzle over. So, Deep Impact's mission finally had closure and had been a resounding success. But this was not the end for Deep Impact. Following in Stardust's footsteps, Deep Impact's flyby was later given a new mission entitled Epoxy, or the Extrasolar Planet Observation and Deep Impact Extended Investigation, which in 2007 saw it heading off to investigate other comets and taking hundreds of thousands of photos before ultimately dropping out of contact in 2013. But by then, Deep Impact had already done significant amounts to advance our understanding of comets and our solar system. What about Stardust? After its extended mission, scientists saw that there was still a little fuel left in its tank, so it ran with it. Firing it for as long as it could, scientists checked to see if their models of how much fuel Stardust held matched up with the reality. To its last breath, Stardust kept doing science until the end. When at last all its fuel was used up, it sent one last transmission to Earth to acknowledge that it was being turned off for good. Now, it finally rests among the stars. Comets are truly fascinating things, and it was thanks to the incredible work of the Stardust probe and the Deep Impact mission that we were able to learn a great deal about their inner composition and workings. While still retaining their beauty, we have pierced through their layers of enigma. We understand that they are not some foreign visitors, but originate here, from our own solar system, and may have even led to the blossoming of life itself on this planet. And it was human ingenuity and precision that allowed these discoveries to be made. So, the next time you see a comet, with its beautiful tail flaring out across space away from it, it will no longer be quite so mysterious or foreboding. They may even be the reason you are here today. And all it took to learn this was to catch the dust from one and to punch another really, really hard. Our beautiful blue planet only has one moon, and it is a battered and sorry looking thing. It has obviously been impacted many times, smashed into with enough force to leave craters so big that we can see them just by looking up into the night sky. But this may not have been a slow siege or a gradual bombardment by the cosmos on the moon's scarred surface. Rather, it was a blitzkrieg. Evidence from the moon's surface suggests that these impacts may have all happened within a very cosmologically short period of time. A surge of falling meteorites that swept across the moon in an apocalyptic rain. Scientists have named this event the Late Heavy Bombardment, and while it is a theory, it would have been a truly devastating period of history with some surprising consequences. It may be the reason we are here today at all. But if it truly happened, what caused it? And if the moon was so scarred, how did the Earth avoid the same fate? I'm Alex McColgan, and you're watching Astrum. Join me today as we journey back in time 4 billion years into the past to unravel a story of chaos around our newly formed sun as its planets settle down into the orbits that we are now familiar with. When the Apollo astronauts came home from the moon, the rocks they brought with them told a surprising story. The astronauts had brought home samples containing impact melt, rocks that had superheated into magma due to being hit by a meteorite, which had, later, gradually cooled back into solid form. But while the Apollo team had collected these reconstituted rocks from different areas and craters on the near side of the moon, almost all of them were dated to around 4.1 to 3.8 billion years ago, with very few showing older impacts. The implication? For some reason, during this period of roughly 500 million years, there was an abnormal spike in falling meteorites that crashed into our moon. This idea came to be known as the Late Heavy Bombardment. This idea is controversial, and not everyone agrees that it happened that way. Such is the nature of scientific debate built on limited evidence. We don't get to go to the moon very often to collect more samples, so it's hard to tell if some process has been muddying the waters. But if the Late Heavy Bombardment happened, what could have caused it? And to answer that, we need to consider conditions back at the dawn of our solar system. It is a well-known idea that our solar system was formed from an accreting disk of intergalactic dust and matter 4.6 billion years ago, circling around a gravitational center that would, later, house the Sun. Gravitational disturbances caused some of this dust to bunch together, and once that happened, each larger ball of matter found itself snowballing in size. Larger clumps had larger gravitational pull, which pulled in more mass to grow the clumps. At this point in history, the vast, spinning disk of matter from which our whole solar system was created had clumped together into planetesimals. These were further attracted to each other, crashing together to form the planets we know today. Within a mere 100 million years, this process of planetary accretion had gathered up almost all the material nearer to the Sun to form what we call the terrestrial planets: Mercury, Venus, Earth, and Mars. One of these impacts formed our Moon, flinging a huge lump of molten rock into space, which formed into a sphere and cooled, and has remained in orbit around our planet ever since. There would still be some isolated leftovers between these planets. Some are still out there today, like the 1.5 million floating asteroids orbiting the Sun between Mars and Jupiter. But this process had pretty much cleared out everything in the inner solar system. But under this idea, you might expect to have more impacts at the beginning, but fewer and fewer impacts as time went on, not a sudden spike. So why could there have been a surge in impacts 4.1 billion years ago that gave our Moon such a beating? That has created quite a puzzle for scientists, although some now think they may have solved it. The finger of suspicion points towards Jupiter, the largest planet in our solar system with more than 2.5 times the mass of all the other planets combined, and the first to form, along with Saturn, as our solar system took shape. If you would like to learn more about Jupiter and its influence on our solar system, check out this video. The suspected behavior of Jupiter is key to explaining the observations that have led to the proposal of the late heavy bombardment theory. Jupiter is not thought to have always orbited at a distance of 768 million kilometers from the Sun. Initially, Jupiter moved inward towards the Sun, reaching roughly where Mars orbits now, as Mars and the other planets didn't exist there at that point, only to then change direction and pull away again. All of this possibly happened within just hundreds of thousands to a few million years. What made Jupiter behave like this? The short answer is its relationship with Saturn. When Jupiter formed, there was still a huge amount of gas swirling around our developing Sun. This gas dragged Jupiter along towards the center of the newly forming solar system. Once Saturn had formed, it also joined this death ride towards the Sun. However, the two new planets bonded as their gravities combined, and the sudden tug of Saturn behind it was enough to arrest Jupiter's grand precession towards the solar system's inner territory and to gently pull it back to the orbit we see it at today. But this precession was not without impact, quite literally. Our asteroid belt, with its 1 to 2 million asteroids, potentially only represents less than 1% of the matter that used to be there. So when Jupiter came sweeping through with its massive, far-reaching gravitational pull, a lot of orbits became disrupted, and many of those objects started to fall inward. Two types of asteroids were brought into this process, from both the inner and outer solar system. This fact becomes quite important later. Not all asteroids are the same, and you may be familiar with the terms S-type and C-type asteroids. S-type asteroids are the stony asteroids from the inner solar system, mainly made up from silicate materials and nickel iron. They are drier because they come from closer to the Sun. C-type asteroids, the chondrite or carbonaceous asteroids, are the most common and are among the most ancient objects in our solar system. They come from the outer asteroid belts, and they contain much larger amounts of something that would later prove crucial to our planet: water. And all of these asteroids began to fall through the patch of space our planet was orbiting. So, to answer my initial question of how the Earth avoided all these asteroids when the Moon was constantly apocalyptically bombarded, it didn't. The timing of this, as far as our planet is concerned, was crucial. By then, the surface of the Earth had cooled to form a more stable crust, what we know as the lithosphere today. This insulated anything above from the enormous heat of the magma below. The magma near the surface was much hotter than it is today, around 1600 degrees Celsius, and it was much more liquid. Heavier elements, especially iron, had sunk towards the central core, leaving the lighter elements and minerals at the surface. As the asteroids rained down onto the surface, they brought with them a whole range of elements and minerals that would remain as part of this surface layer. It is now thought that many of the important deposits we find at the surface today, ores and metals such as lead, nickel, copper and gold, were brought here in this way. More important than valuable metals, however, was the arrival of water. Vast amounts of water. Had all this water arrived earlier, when the surface of our planet was hotter and less able to maintain an atmosphere, much or all of this water would have escaped back into space, possibly leaving the planet an arid desert like Mars and the Moon. Surrounding Earth during the bombarding chaos 4 billion years ago was a toxic atmosphere of methane and ammonia, covering an unstable but solidifying surface of basalt-type rock, dark grey, almost black in colour, and with brightly glowing lava erupting through faults where it was shattered by the incoming hailstorm of asteroids. Steaming oceans of water were forming, helping to further cool the developing surface, a true vision of hellfire and brimstone. It is partly because of this churning nature of the surface, floating on liquid magma, that today we see no trace of the craters left by these impacts. The forming lithosphere was fractured into many small tectonic plates that moved around and recycled themselves much faster than they do today, and no trace of these early rocks remains. The oldest surviving rock formations on our planet roughly mark the end of the Hadean period, and by this time, this intense bombardment of our planet had likely come to an end. The end of the Hadean era also marks the beginning of a new development in our planet's fascinating history, the story of life. It has long been debated how the very beginnings of life may have evolved on Earth. Key building blocks would have been needed, like hydrocarbons and other complex molecules. What conditions could have led to the origins of this organic molecular soup? Interestingly, while there is debate over the reality of the late heavy bombardment, this theory does help to answer this vital question. It is now known that all 5 of the essential building blocks of DNA and RNA exist in space, and have been found on meteorites. But while the meteorites we see today burning up in the night sky as they enter our atmosphere could never bring anything as delicate as these molecules to the surface of our planet, they would burn away to nothing before even reaching the stratosphere. But when much larger objects from space were raining water and ice onto our newly formed surface, it is certainly possible that they seeded the Earth with some of the right ingredients that made life viable. There is compelling evidence that life began at the very time when this bombardment was ending and new oceans had formed. Finding the answers to many of these questions is almost impossible on Earth, because so little remains from this time. This is why scientists are so keen to study clues that may still exist on the Moon. The reason why this evidence is so well preserved on the Moon is that, unlike on Earth, the surface of our Moon was already quite stable, without the churning and recycling of the surface that occurred here on Earth at that time, so the craters remain intact. Also, the surface of the moon is not being constantly eroded by weathering. There are no seas to grind it down, no wind and acid rain to wear away the rock. The dust that covers the surface is pulverized rock that remains undisturbed following those dramatic impacts from billions of years ago. There are craters on our planet's surface, such as the Barringer crater in Arizona, USA, but that dates only from 50,000 years ago. Of the late heavy bombardment era craters themselves, there is nothing visible at the present time. If such craters do survive somewhere on our planet that have not been completely eroded away, they could be buried under later sediments or lava flows, and we may never find them. We've been able to make progress in our understanding of this era thanks to the astonishing 382 kilograms of moon surface rock brought back to Earth from the Apollo missions. Radiometric dating of these rock samples indicated that they were last molten during a narrow period of time around 3.9 billion years ago, consistent with when we believe that Earth and other inner planets were being bombarded by asteroids. Those large craters you see on the moon are where asteroids have impacted the surface, and when lava has flowed out, forming those characteristic smooth craters that we can see on clear nights. Not everybody agrees, however, and as more refined analytic techniques have been developed over time, questions have been raised about the timescale and duration of this period of asteroid activity. Some dating inconsistencies suggest that the craters may have formed over a much longer period of time, tailing off from the planetary accretion that formed the terrestrial planets rather than a more concentrated period of activity. The sample materials that scientists have available from the Apollo missions are still limited, as they stem from just a few carefully selected locations. More samples from future missions will hopefully resolve some of those controversies, and the NASA Artemis missions could see another landing on the surface of the moon as early as 2026. I can't wait to see what new discoveries this could bring. The late heavy bombardment theory may not be a perfect explanation, but it tells a convincing story that fits our observations of the moon and of the parts of our planet's surface that we have explored so far. And it provides some possible answers to the question of how such a vast amount of water came to exist on the surface of what had once been a molten ball of rock. Whether or not this turns out to be the correct story, next time you fill the kettle or paddle in the sea, you might remember where that water came from and how lucky the timing of it all must have been for it to actually stay here and create a planet so conducive to life. I hope you will join me for the next video in this series when we will explore another chapter of the incredible history of our beautiful blue marble, planet Earth.
The moon may seem like a barren, uninteresting world. But take a closer look at its surface and you'll find many interesting puzzles about its past which are just waiting to be solved. The LRO, or the Lunar Reconnaissance Orbiter, has been scanning the surface of the moon since 2009, taking super high resolution shots of its surface from various angles, giving us a view of the entire moon like never before. In the last episode of this series, we looked at the mountains on the moon, and today we will look at some of the most interesting craters found on its surface. I'm Alex McColgan and you're watching Astrum, and together we will explore the surface of the moon and give you a view and understanding of our close neighbour that perhaps you've never had before. Because of the many surveying missions to the moon over the years, the entire moon has been mapped out, and you can view all the data obtained in a program called QuickMap, which I will post a link to in the description in case you want to check it out for yourself. Zooming out as far as we can go, on the far side of the moon we can find one of the biggest impact craters in the solar system, the Aitken Basin at 2,500 kilometers across. which is interestingly where the Chang'e 4 Chinese mission landed in January of this year. The LRO was even able to image the rover from space. But without the rover as a size guide, what you may immediately find unusual about the lunar surface is the complete inability to judge distances and scales for the images you are looking at. This is due to the lack of an atmosphere, the haze of which helps us judge distance on Earth, and things we are used to like trees and buildings, which help us judge scale. So I will always try and include some visuals to help you see how big something is in this video. As you can see, the surface of the moon is littered with craters. It doesn't matter where you are on the moon, there will be craters of various sizes. This implies that the surface is old and hasn't been renewed by lava eruptions from the mantle anytime recently. The most recent eruption thought to have happened 1.2 billion years ago. There are an estimated 300,000 impact craters over 1 kilometer across on the surface of the moon facing us, and millions more smaller than that, like the ones you are currently looking at. The moon can have such small craters because it has no atmosphere, meaning every meteorite heading for the moon will hit its surface. On Earth, most meteors burn up in the atmosphere. Just imagine how many shooting stars there are each night. Were it not for Earth's atmosphere, every one of them would impact our surface too. What's interesting about each crater you see here is that you can roughly estimate how old a crater is by how eroded it is. Craters which appear very smooth are much older than craters with lighter substances surrounding them, with sharp and defined edges. The bright patches haven't had so long to have a weathering effect happen on them. But weathering on the moon? How can that be? Well, this weathering is not caused by water or air, but rather by tiny micrometeor impacts and intense radiation from the sun, which dull the thin outer layer of the moon. If we speed along to the end of this image, we can see a relatively fresh crater only a few hundred meters across. Using LRO's narrow-angle camera, we can see a close-up view of the effects of such an impact on the lunar surface. These linear patterns are the effects of the ejecta from the impact. Finer dust would have been blown across the surface with some force. Larger boulders not quite making it as far, although leaving a trail from where they rolled away from the impact. The crater itself isn't super clear in this image due to the time in the lunar day this was taken, the sun close to the horizon, casting long shadows across the surface, although you can still see fresh exposed material along the crater wall. Comparing this to an old crater, here you can see a much smoother and darker looking crater, although still brighter than the heavily weathered surface in the surrounding area. What I like about this image though, is that zooming in, you can see some ejecta that landed from another impact off the image. Here's a boulder that landed on the crater wall and then rolled halfway down. The only thing with these top-down perspectives is that you don't get a great concept of depth in the image. How shallow or deep can craters get? Luckily, the LRO doesn't just scan the surface, but can take more oblique shots of the moon too, which can definitely help us appreciate depth. Look at this fantastic image. The crater is around 21 kilometers across, and it has some fascinating details all around it. Again, we can see the trails left by huge boulders rolling down the slopes, and very bright walls implying it is a young crater, yet darker material at the base. The contrasts are really quite vivid, and it almost looks like some parts could have been liquid at some point. The impact would have initially melted the rock into lava, which flowed to the bottom, collecting in pools which have since solidified. The impactor was likely 2 kilometers in diameter and hit the moon 10 times faster than the speed of a bullet. That would have been some collision indeed. Another great image I have to show you is this. A crater 10 kilometers across, What's special about this one is its interestingly raised rim. This is another example of rock melting from the impact, but rather, this time, slopping beyond the rim and flowing down before solidifying again. If we look closely around the crater, you can also see ejecta scattered across the surface, disturbing the ground and leaving brighter patches exposed. See? Once you know what you are looking at, even the moon becomes very interesting. But these have been very pristine craters. What if a meteor lands somewhere a little less conventional? Here is a crater within a crater. The impactor hit the wall of the larger crater, meaning it has quite an unusual shape. Although, from a top-down perspective, it still looks quite circular. Just as a side note, this image is a true color image of the moon. Most other images of the moon are taken in black and white to save bandwidth. Astronomers prefer resolution over color, although the lowest resolution camera on the LRO is capable of color, and this is an example of it. But certain craters can be unconventional in other ways too. There's a little understood phenomena on the moon that scientists have so far struggled to explain, and that is cold patches found on the moon after the sun goes down. So far, we have really only focused on the cameras equipped on the LRO, but it has a host of other instruments on board, including the Diviner Lunar Radiometer Experiment, which has mapped the moon's surface temperatures. There are 2,000 points on the moon that cool down more than the surrounding areas when the sun goes down. When the sun rises on the spots again, they normalize their temperature and quickly blend in with the background. The only thing these spots seem to have in common? They are always found around young craters, no smaller than 50 meters and no bigger than 2.3 kilometers. But the spots themselves are much larger than the craters. Here is a heat map of the crater I was just showing you. White is the hottest parts of the image, blue is the coolest. As you can see, a large cool region surrounds the young crater. There is an ongoing investigation to find out the cause. What do you think it could be? There really were so many more images I could have shown you today, but I'll have to save them for next time. I just wanted to leave you with one final image that I found breathtaking. This crater, found near the south pole of the moon, is almost always in shadow. The sun never rises high above the horizon here, meaning only the peaks of the crater stick out enough to be enveloped in light. What you are left with is a stunning contrast, almost like the yin and yang symbol. This is certainly my new desktop background image. But this region isn't just an eerily beautiful place, but it is actually one of the candidates for the future Artemis mission to the moon. The lunar South Pole is of particular importance to future human missions, as there is thought to be millions of tons of water ice to be found in this region, at the bottom of craters like this, forever protected from the sun's rays. If there is to be a future colony on the moon, this is roughly where it would be located. So, there you have it, a sample of some of the most interesting craters on the moon.
If I were a superstitious man, I would advise you to be careful what you call your space missions. When Russia named its first mission to the moon in 47 years, it was originally given the designation Lunar Globe, translating in English to Lunar Sphere. However, this name troubled scientific director of the Space Research Institute of the Russian Academy of Sciences, Lev Zeleny. Glob was too similar to a different Russian word, grob, meaning coffin. Zeleny changed the name of the mission to Luna 25, intending to call back to the earlier Soviet lunar missions, which were the last time Russian spacecraft successfully landed on the moon. But perhaps it was too late, and something of that original name lingered, because we now know that Lunar Coffin was a much more apt name for the ill-omened Luna 25. I'm Alex McColgan, and you're watching Astrum. Join us today as we explore the fate of Russia's first moon mission since 1976. For the country that once led the world in the space race, what exactly went wrong? Although we often look at NASA or ESA missions here at Astrum, Russia's space program has historically been quite the powerhouse. Back when Russia was part of the USSR, it was the Soviet Union's launching of Sputnik 1, the first artificial satellite, that triggered the space race in 1957. And for a time, the Soviet space program went from strength to strength. It was the Soviet Union that put the first man into space, and the first woman, the first multi-person crew, the first dog. Their rockets escaped the Earth-Moon system first, impacted the moon first, orbited the moon first, took photos of the far side of the moon first. Soviet cosmonauts did the first spacewalk. The USSR launched the first space station. To the eyes of many and to the pleasure of Soviet leadership, the USSR was winning the space race. But beneath the surface, not everything was going as smoothly as it appeared. The Soviet Union also saw the first death during a space mission, when the re-entry capsule's parachute of cosmonaut Vladimir Komarov failed to open on his re-entry to Earth. The only 3 men to have died in space were a crew of Soviet cosmonauts visiting that first ever space station. Soviet launches were plagued with failures, but eager to look good in the eyes of the world, particularly compared to its rival, the US, the USSR simply didn't report any of its failed lunar missions. It pretended any rocket that didn't make it out of the atmosphere was never intended to be a moon mission at all. In reality, only about 34% of Soviet moon missions ended in success, in comparison to America's 60% success rate on equivalent missions. America landed the first man on the moon in 1969, and after that crowning achievement, both superpowers seemed to lose interest in continuing the race, refocusing their space programs towards non-lunar pursuits by the mid-1970s. Soviet cosmonauts never set foot on the moon itself. The USSR cancelled any of its plans to do so, as the endeavour was ultimately seen as too expensive. Perhaps more importantly, what was the point of going if you were only going to get there second? But with the turn of the millennium, and since the fall of the Soviet Union in 1991, the world's interest in going to the moon has been rekindled. Scientists realized that the moon would make a good stepping stone for human space missions to Mars, due to its plentiful resources, such as newly discovered water ice, ideal for rocket fuel, air and water, and low gravity. Resources on the moon began to attract the attention of businesses for economic reasons, and nations began to consider setting up permanent bases on its surface as a way of turning a profit. And of course, there is still a lot of science to be done there, attracting those who wish to learn more about the processes by which the moon formed and the cycles that govern it. Russia's old rival, the USA, rose to dust off their space programs. America started its Constellation program in 2005, declaring their aim to go back to the moon. But now other nations were getting in on the act too. India, who had not been part of the first race for the moon, began its Chandrayaan program for lunar exploration in 2000. Governments across the world believed that the benefits of going to the moon in this second rush were so great, nations who didn't go would in some way fall behind. In the words of ISRO chairman Krishnaswamy Kasturirangan, it is not whether we can afford it, it is whether we can afford to ignore it. Russia did not intend to be left behind. It was eager to pick up the Soviet legacy of space exploration. In fact, it beat its competitors to the punch. Russia had already begun thinking about a new lunar mission as early as the mid-1990s, when scientists Mikhail Mavrov and Eric Galimov put forward their proposals to Roscosmos, Russia's newly restructured space agency. Their Lunar Glob mission was approved and was initially intended to have a lot more parts to it, including a penetrator for seismic sounding, a lander, and an orbiter. However, the project initially did not have enough political will behind it. It faced budget cuts after the Russian financial crisis of 1998, when the ruble lost over 2/3 of its value in 3 weeks and was marred in delays that repeatedly knocked it back and put it on hold. The penetrator and orbiter were scrapped, leaving just the lander, as the plan for the mission was reimagined to make it more economical. Russia wanted to be a nationally recognized player in the space game, but didn't want to spend massive amounts of its budget on the plan. In 2005, Russia only invested 20 billion rubles, or about $700 million in its space industry, compared to the USA's $15.6 billion. One way to work around this was to collaborate with other nations. Russia initially tried to work with India on the Chandrayaan-2 mission in 2007. Luna 25 would fly with India's orbiter and be the mission's lander. However, this low spending ultimately punished them, and Russian scientists were unable to get the lander's technology working in time for the initial 2013 launch date. India eventually abandoned the collaboration and completed Chandrayaan-2 on their own. Russia was left trying to get Luna 25 to the moon's surface solo. India's Chandrayaan-2 lander crashed into the moon, but India was eager to try again with Chandrayaan-3. This set Russia and India on a course from collaborators to competitors. Both Russia and India were interested in the moon's south pole, where Chandrayaan-2 and others had confirmed through spectrometry the presence of water ice. Luna 25 and Chandrayaan-3 were now racing to be the first lander to successfully touch down on the moon's south pole and potentially discover that water ice. However, Russia faced a new problem: the invasion of Ukraine in 2022. Western countries were outraged at Russia's decision to attack its neighbor and came together to impose massive sanctions. Not only was this painful economically, but one vital element of these sanctions was a ban on the trade of high-end computer chips and components. These would prevent Russia from developing high-precision ballistic rockets for use in its military, but hit Russia's lunar goals too. European scientists began ending their collaborations with Roscosmos. In an interconnected world where Russia traded for much of its high-end components, Russia would now have to go it alone. India completed Chandrayaan-3 and launched it on the 14th of July 2023, a mission we covered in greater detail in a previous video. However, the route that they took to the moon was a fuel-efficient, but time-inefficient one. It would take over a month to actually arrive on the moon's surface. India estimated a touchdown date on the 23rd of August. If Russia really hurried, it could complete its lander and arrive before India by taking a shorter, more fuel-intensive route using Russia's powerful Soyuz 2.1B rocket. The Luna 25 mission had, by this time, been delayed from 2021 to 2022 and then to 2023. In a bad stroke of luck for Russia, its BIB navigation sensor didn't pass quality tests. This was problematic, as the BIB sensor relied on a computer chip normally supplied from the West, a chip that Russia could no longer purchase due to Western sanctions. So Russian scientists had to develop a new one on their own, the BIAS-L. Luna 25 was cleared as ready to launch on the 11th of August 2023. It had 8 Russian scientific instruments on board, including laser mass spectrometers, infrared spectrometers, cameras for imaging the lunar surface, and even a device for measuring dust and micrometeors. Luna 25 would operate on the moon's surface for a whole year, enduring the freezing cold of lunar nights and the intense solar radiation of lunar days. It had the potential to do some good science. The Soyuz rocket was powerful enough that it would get Luna 25 to the moon's surface by August 21st, 2 crucial days before India's lander arrived. Russia would indeed win the race against its rival. Luna 25 launched successfully from the Vostochny Cosmodrome on the 11th of August 2023 and entered the moon's orbit on August 16th. It took photographs of the moon's surface, imaging the Zeeman crater. All systems were functioning normally, and communications were good. Russian scientists then began to make final preparations for the landing itself. The south pole of the moon is home to some treacherous terrain, and the scientists didn't want a rough touchdown which could potentially harm Luna 25. But then, something went wrong. On August 19th, Luna 25 lost communications with Earth. No longer guided remotely, Luna 25 attempted to perform its own pre-planned maneuver that would take it from a circular orbit around the moon into the new path down towards the surface. However, further failures occurred. The Bias L navigation device, the one developed by Russian scientists after the previous one hadn't passed quality control tests, had sent bad information to the ship's onboard control unit. As a result, the thrusters fired for 127 seconds instead of the intended 84 seconds, pointing Luna 25 into a steeper and steeper descent. On the 20th of August, Luna 25 careened down towards the moon's surface at a pace too fast to stop. Roscosmos scientists could do nothing but look on in horror as the lander hurtled into the terrain, traveling faster and faster. Although no external cameras witnessed the impact, it's easy to imagine the grim result of acceleration under gravity that turned Luna 25 back into a lunar coffin. Its lunar mission had not lasted a year, but only a few days. NASA's Lunar Reconnaissance Orbiter did a flyby later, taking an image of the site of the craft's final resting place. Luna 25 had impacted hard, creating a crater about 10 meters in diameter. Russia had attempted to show the world that it was still a great power when it came to space exploration. However, Luna 25 had been mired by pressures and challenges. Western sanctions had indirectly sabotaged it. The Russian replacement ship was not precise enough, or was not hardy enough to survive the high radiation environment of space. However, Russia's attempt to beat its rival India had also created problems for itself. When I learned about its arrival date being 2 days before India, it reminded me of a similar time when the Soviet Union's Luna 15 mission crashed into the moon only a few hundred miles and on the same day as Apollo 11 landed. Luna 15 had been tasked with collecting moon rocks, the same as the astronauts of Apollo 11. And although it was unmanned, if America's mission had failed, it would have been a point of pride to the Soviet Union that Luna 15 had managed to steal Americans' thunder. This was political point scoring. The Soviet Union didn't want to just get to the moon. It wanted to get there first. And inevitably, when you're racing to beat someone else, you take less time making sure everything works as well as it needs to. And so, you run a greater risk of failure. Ultimately, just like with Luna 15, Russia's Luna 25 had the opposite effect that its country's leadership intended. Rather than show Russia's superiority in space exploration, it showed the downsides of isolationism and rivalry over collaboration. If Russia still was working with institutes like ESA and shared in technological advances, perhaps it would be boasting a success right now. In many respects, it's a tragedy. Perhaps this can one day change. The future of mankind seems pointed towards the stars. If we are to thrive out there, it will be because we as a world work together. The tragic fate of the Luna 25 mission can and should be a learning experience, not just an embarrassing footnote in history, but only if the right lessons are drawn from it. Pride is not always a good thing. Rivalry can leave us isolated when we don't need to be, and can prevent us from thinking things through. Although it's unlikely, it would certainly be nice if our efforts to prove our superiority to each other could finally be put to rest, buried in a frozen coffin on the lunar surface.
Mars is littered with craters. Although Mars has an atmosphere, this atmosphere is very thin, meaning even small meteors manage to impact the surface before they burn up. The high-rise camera on board NASA's Mars Reconnaissance Orbiter has been able to image a lot of these craters in exquisite detail, meaning we can examine craters on another planet like never before. I'm Alex McColgan, and you're watching Astrum, and together we will look at some of Mars's most interesting craters, and I'll explain what it is you are looking at. We will start small. Here is a very small and very fresh crater that likely formed sometime between 2006 and 2008. New craters have some very distinct characteristics, specifically defined crater walls and evidence of fresh ejecta. Although this crater is just a few meters across, you can see the ejecta spread out over hundreds of meters. But this is over a flat surface. What if a meteor hits a slope? Well, that's exactly what happened here. The dust on Mars is extremely fine, meaning it can move quite easily. You can see the recent impact crater on this slope here, which caused an avalanche of dust down the slope. The area around the avalanche looks fuzzy because ejecta also spread out around the impact site. The dust is clearly precariously balanced, as there have even been smaller avalanches seen a little bit higher up. So, if an impact caused this avalanche, what caused it in these large craters? What you are looking at here is slope streak formation, one of the few active geological processes on Mars that we know of. We don't exactly know why these streaks are formed, but the leading theory is that due to the tiny size of Mars's dust particles, the smallest trigger, like a gust of wind, can make the dust tumble and act like a fluid, like in a snow avalanche on Earth. The darker streaks are the youngest, the whiter streaks are older, the brightening caused by dust settling on them over time. It is quite the beautiful sight. Let's move on to a particularly flat area of Mars. This area is quite boring and featureless, but zooming out a bit, we come across this big, kilometer-wide crater, which seems to have a scar on one of its walls. This is actually caused by lava flowing down from the lowest point in the crater wall. The lava coming from a nearby volcano that has repeatedly covered this area in lava from its eruptions. That's why the surrounding area is quite featureless. This used to be a large lava plain back when Mars was more geologically active. That makes the surrounding area here the youngest surface on Mars. I can only imagine what this area once looked like. The game "The Floor is Lava" would be quite apt. Let's have a look at another crater heavily influenced by lava. This is Elysium Planitia, the second largest lava plain on Mars. This 3D view, acquired from a stereo pair of images, shows the basin of this crater is very flat. This is again due to lava flowing and filling the area from this vent found in the center of the crater. This is an old, inactive vent now, meaning the surface hasn't been renewed for some time, evidenced by the many craters dotted around the basin floor. There's another really curious crater I want to have a closer look at. This bizarre crater is found within the big Schiaparelli crater, and it kind of looks like a giant bullseye. We don't really know why it's formed like this, although it could be due to there being sedimentary layers in the bedrock that have been eroded smooth, or it could be that this is actually a flat surface, which just appears concave because the crater has been filled up by sedimentary deposits over time, meaning the innermost layer would also be the youngest. We don't have a stereo view of this crater, so we can't tell either way right now. What about craters that haven't been filled up by one thing or another? This is Pallica crater, a several kilometer wide crater that has also had the 3D treatment. This crater is pretty deep, stretching several hundred meters down from the rim. And along the crater wall you will notice what looks to be old water channels flowing down the bank. While liquid water can't exist on the surface of Mars, it is theorized that water could still flow under Mars's surface. Salty water that flows out of the ground could make its way down a steep slope like this for a little while before it evaporates. On a different crater, this flowing has been observed. Notice the differences over the years. Although we haven't confirmed this process is due to water yet, even if it is the leading theory, it could still just be fine dust that flows down the slope. Let's have a look now at a very old and deep crater. At first glance, you can see inflow channels going into the crater, and that it was once even deeper than this, but it has since been filled somewhat by sand dunes. Zooming in, we can see the sedimentary layers near the crater walls. Had this crater not been filled in by sand, perhaps it would resemble the previous crater we looked at in Schiaparelli. Somehow this crater's age just makes it look even more impressive. For the last crater we'll look at today, we'll have a look at another 3D view. This unnamed 15-kilometer wide crater is found in the Domani region, and seeing it from this angle is quite the sight to behold. Going over the crater walls, you'll notice this crater has 2 tiers of walls, and some peaks in the center. This is due to the size of the crater. Smaller, simple craters tend to have smooth walls all the way down to the basin. Larger ones have tiered walls with uplift at the center. They are known as complex craters. Usually complex craters would be too big to fit in a high-rise image, but this is a combination of several images, which gives us an unprecedented view of such a large Martian crater. Coming closer to the crater walls, you'll again notice these water channels coming down the side. You'll notice the smooth appearance of the terrain, which implies dust has had a lot of time to settle here. So, there you have it, some of the most interesting craters on Mars. There are a lot more that I could have talked about, but sadly they will have to wait for another time.
Thanks for watching. This video was in part made possible by all the astronauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.